In this lesson, we're going to learn about the fundamental identities. But first, let's talk about what an identity actually is. So before we can do that, we need to talk about different types of equations. The one that you're most familiar with probably is what's called a conditional equation. This is an equation that's true for a countable number of solutions. Generally, the cases that you run into are one solution, two solutions, maybe a few more than that, but generally you can count the number of solutions. So it's not necessarily finite, but it's countable. So for instance, 2x plus 7 equals 25. This is a conditional equation. And you know very well at this point what to do to solve that. So if you come off to the side, subtract 7 from both sides of this equation, then you have 2x equals 25 minus 7 is 18. Divide both sides by 2, you get x equals 9. So there's one solution. So I can count the number of solutions. So it's a conditional equation. So it's a true statement on the condition that x is equal to 9. That's the only time that it's true. Other possibilities, contradiction, an equation that's never true. So for instance, 6 times the quantity 1/3 x minus 10 equals 2x plus 4. Because what happens here, if I distribute the 6 into these parentheses, I end up with, so 6 times 1/3 is 2x. 6 times negative 10 is negative 60, equals 2x plus 4. Now if I subtract 2x from both sides, the 2x's cancel out on both sides, and I'm left with negative 60 equals 4. Which is not a true statement. It's never a true statement. So this is a contradiction. And what that means is that there's no solution to this equation. So a contradiction has no solution. It's never true. Lastly, we have an identity. An identity is an equation that is always true. So for instance, 6 times the quantity 1/3 x minus 10 equals 2x minus 60. So again, if I distribute the 6 into these parentheses, I get 2x minus 60 equals 2x minus 60. If I subtract 2x from both sides, the 2x's cancel away just like they did last time. But what's different is now negative 60 is in fact equal to negative 60. And I could add 60 to both sides and I'd end up with 0 equals 0. Either way, this is a true statement. It's always true. There's no value of x that you could put into this equation that would result in a false statement. So that's what's referred to as an identity. In trigonometry, we actually have a lot of different identities, and you've seen some of them. Most of what you've seen are called the fundamental identities. So let me bring those up for you. You've seen the reciprocal identities. So sine of theta is equal to 1 divided by cosecant theta. So sine and cosecant are inverses of one another. They're reciprocals, that is. So that's one of the reciprocal identities. Cosine theta is equal to 1 over secant theta. And tangent of theta is 1 over cotangent theta. We also have the quotient identities, which involve tangent and cotangent. So tangent of theta is equal to sine theta over cosine theta. Cotangent is cosine over sine. We've also seen the Pythagorean identities, starting with sine squared theta plus cosine squared theta equals 1. Tangent squared theta plus 1 equals secant squared theta. And 1 plus cotangent squared theta equals cosecant squared theta. Now, we've looked at the derivation of all of these, so I'm not going to go into that this time. But I just want to remind you, these last two Pythagorean identities are difficult to remember, but what I do is I always remember the first one, sine squared plus cosine squared equals 1. if you take each term and divide it by either sine squared or cosine squared, you're going to end up with one of the other ones. Because sine squared divided by sine squared gives you 1. Cosine squared over sine squared gives you cotangent squared. 1 over sine squared is cosecant squared. If you divide it through by cosine squared instead, you'd end up with tangent squared plus 1 equals secant squared. So I don't often have at my fingertips exactly what the last two Pythagorean identities are, but I know that I can derive them if necessary. Some other identities, which a lot of textbooks refer to these as fundamental identities, but I don't myself call them fundamental, simply because I don't really see that they get used a whole lot. They are useful, so I'm going to bring them in here, but you won't find them nearly as useful as the ones I previously mentioned. These are called the negative angle identities. And the negative angle identities look like this. So sine of a negative angle is equal to negative sine theta. So if you take sine of 45 degrees, for instance, then that results in positive square root of 2 over 2. But if you take sine of negative 45 degrees, you're going to get negative square root of 2 over 2. You get the exact same value, but just opposite in sign. So any angle measure that you use there, if you put in the negative of the angle instead of the positive, you're going to get the opposite sign that you would have. That's just how the sine function works. Cosine is similar, but it's a little bit different. The cosine of a negative angle is equal to the positive of the cosine. So it doesn't matter if you put a negative angle in, you get the exact same result back out. The remaining trig functions operate in basically the same way as the first two. And you can use the other fundamental identities to prove each of the remaining ones. But I'm going to show you an applet that will help you understand what's happening with negative angles in terms of sine and cosine. The remaining ones are fairly easy to show. Like for instance, if you know that cosecant of, if you're looking for cosecant negative theta, for instance, and you know that cosecant is 1 over sine, and you know that sine of negative theta is negative sine theta, well, that then results in negative cosecant theta. So the remaining trig functions are relatively easy to prove based off of sine and cosine. But let's take a look at what happens with sine and cosine themselves. Okay, so let's first start with the graph of sine. So let me show that to you. So the graph of sine is our normal sine wave. And what I have here is, I have a point, there's actually 2 points here. One is called P and the other one's called P1. You can't see them because they're mapped on top of each other right now. You can't see the 2 different points. However, if I move point P, so I'm moving point P now, P1 moves in the opposite direction. So what's happening is, whatever angle measure I have for to put into the sine function, this angle measure is the opposite. So notice, if I put a negative angle measure in, if the sine is positive, the sine function is positive, that is, then if I put the opposite of that angle in, the sine function results in a negative number. And that's always going to be the relationship between these two values. Let me go up to a common angle measure. So let me go to pi over 2. So if I drag my point over here to pi over 2. Now, the angle measure at pi over 2, when I plug that into the sine function, the result is positive 1. If I put negative pi over 2 in, I get negative 1. So I get the opposite sine It's unfortunate that I have to say the word sine and refer to the sine function, and sine and refer to positive and negative in this case. But I get the opposite signed number here. Okay? And if you continue on, what you'll also notice is whenever you have an angle measure where the sine function results in a negative number. So now notice P here for this angle measure theta is resulting in a negative number for the answer. Well, I don't want to make it look like theta, so it's negative. Now, the opposite angle measure, so this is negative theta, it's now resulting in a positive answer. So what that means is no matter what the sign of the result of the sine function is, you're going to get the opposite sign as your answer. So if you put, so in general, sine of negative theta is equal to negative sine theta. So no matter what angle measure you put in, if you put the negative of that angle measure in, you're going to get the exact same value as the sine function would normally give you, but it's going to be the opposite in sign. All right, let me show you cosine then. So cosine works similarly, but it has a different type of symmetry. So it has a symmetry that is about the y-axis. And so what that means is you have the exact same image of the graph on the right-hand side of the y-axis as the left-hand side. So that's the reason why any angle measure you put into cosine, so whatever this angle measure is, theta, if you put in negative theta, you get the exact same answer out. So the exact same y value comes back out. And it doesn't matter how far along you go out, from the y-axis. The y values are always the same for point Q and point Q1. So if you do cosine of a negative angle, you're going to get the exact same value as if you did the cosine of that positive angle. So the result there is cosine of negative theta is just equal to cosine of theta. Let's look at some examples of how some of these identities are used. Okay, so use an identity to answer this question. So if secant theta equals negative 1.154, then secant of negative theta equals what? Well, we know that secant of negative theta is equal to secant of theta. Secant relies on cosine because it's just 1 over cosine. So it's going to follow the same sort of rule that cosine does for negative angles. Which means if I put a negative angle in, it doesn't really matter. I'm going to get the exact same value. So this is also going to result in negative 1.1524. If this had been, for instance, if sine of theta equals negative 0.2481, then sine of negative theta, well, it results in the opposite sign. So it would have been 0.248, positive 0.2481. So any sine, cosecant, tangent, and cotangent all change signs, but secant and cosine do not. Use identities to answer the following. If sine theta equals 7/9, then cosecant theta equals what? Well, we know that sine of theta is 1 over cosecant theta. And similar, we could say cosecant theta is 1 over sine theta. Means the same thing. So what we can deduce here is to get our answer for cosecant theta is just going to be 1 over that value that I have for the sine of theta. And if I take 1 over a fraction, it just means to invert the fraction. So the answer here is 9/7. Find the value of cosine theta if sine theta equals -2/7 in quadrant 4. Okay, there's a couple of ways I could do this. One is to use identities. Because I know an identity that relates sine and cosine together. So I can, because I know cosine squared theta plus sine squared theta equals 1, I can use this to plug in the value that I have for sine and then solve for whatever cosine should be. So let's try it. So cosine squared theta plus -2/7 squared equals 1. Or cosine squared theta plus 4 over 49 equals, I'm going to go ahead and change this 1 into 49 over 49 because I'm going to need to combine those fractions anyway. Might as well just get a common denominator ahead of time. So now what I can do is just subtract 4 over 49 from both sides. Oops. And when I subtract 4 over 49 from both sides, I now have cosine squared theta equals 45 over 49. And to get cosine by itself, I need to take the square root of both sides. So cosine theta equals the plus or minus square root of 45. The square root of 49 is 7, so I'm going to go ahead and reduce that. But 45 can be reduced. So 45 can be written as 9 times 5. So I can write this as plus or minus 3 square root of 5 over 7. Now, this isn't my final answer because I do have to decide if this answer is going to be positive or negative. And the way that I do that is by the quadrant. So I'm in quadrant 4. So all students take calculus. So this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So that means cosine is supposed to be positive. So the cosine of my angle measure then is positive 3 root 5 over 7. And that guarantees that I have the correct sign of the values, the positive or negative sign, that is. Now, I told you there was more than one way of solving this. The other way is to use right triangles. In most of these kind of questions that you get, you can almost always solve using right triangles. So we kind of have a choice between using right triangles or identities in this particular case. So if I was using right triangles, I know that I'm in quadrant 4, so I'm going to draw a right triangle that's oriented so that it's in quadrant 4. So this might be my angle measure theta, and this would be my reference angle alpha. And remember, the reference angle and the angle itself are always going to have, the same signs dependent upon what quadrant you're in. So the sine of angle theta is given to me as -2 over 7. Sine, if you remember, SOHCAHTOA, is the opposite side over the hypotenuse. So the side opposite alpha is -2, and the hypotenuse is 7. So that just means I need to figure out what this length is right here. And I find that out using the Pythagorean identity. So x squared plus negative 2 squared equals 7 squared. Or x squared plus 4 equals 49. Or x squared equals 45. And if I take the square root, it's plus or minus, again, simplifying the square root of 45, that's going to be 3 root 5. And then I just have to choose the sign dependent upon the quadrant. And if I'm in quadrant 4, this x value needs to be positive. So 3 root 5. Now that I have the other side of this angle, I can now say the cosine of theta, which is the adjacent side over the hypotenuse, I would get 3 root 5 over 7 as an answer. Either way, you're going to get the correct value. Find the value of sine theta if secant theta equals negative square root of 21 over 4 in quadrant 2. Now, the sine and secant don't necessarily have a trig function identity that relates the two, but you can always solve these types of equations using right triangle trigonometry, which just means that's what we have to do in this case. So in quadrant 2, I'm just going to draw a triangle in quadrant 2. I'll call this angle theta and this alpha, just make it a reference angle. And I know that secant of theta is equal to negative square root of 21 over 4. Now, secant is 1 over cosine, and cosine is the adjacent over the hypotenuse, which means secant is going to be the hypotenuse over the adjacent side. So it's going to be square root of 21 over negative 4. Now, how did I know to put the negative with the 4 rather than with the 21, or the square root of 21? The reason is that the radius is never going to be negative. So we have that to work with. So that's the reason I chose it to go there. And also, in quadrant 2, the x values are all negative. And so I knew that this x value was going to have to be a negative number. So my job here then is to solve for the missing y value on my triangle, which means I can use the Pythagorean theorem because this is a right triangle. So negative 4 squared plus y squared equals the square root of 21 squared. And just be careful with these. When you're setting up the Pythagorean theorem, it's always the sum of the squares of the two shorter legs is equal to the hypotenuse. So you can't randomly choose which values go where in the Pythagorean theorem. This one always has to be your longest side. Now, knowing that, 16 plus y squared equals 21, or y squared equals 5. So y equals the plus or minus square root of 5. And knowing that, I just have to choose whether it's going to be positive or negative. And I'm going to choose it to be positive because the y values are positive in quadrant 2. So this is going to be the positive square root of 5. Okay, so to finish answering my question then, I now need to know what sine of theta is. And since I know all three sides of the triangle, I can figure out what sine theta is. So sine theta is the opposite side over the hypotenuse. And the only thing that I need to make sure of is that my this gets simplified. So in order to simplify it, I just need to make sure I get the radical out of the denominator. Your homework's always going to request you to do that. So to get the radical out of the denominator, just multiply the numerator and denominator by the same square root, so square root of 21 over itself. 5 times 21 is 105, and the square root of 21 times the square root of 21 is just 21. And that takes care of it. So that's my final answer. And just to double check to make sure I have the correct positive or negative sign, just remember, whoops, all students take calculus. So all students take calculus. So sine and cosecant should be positive in quadrant 2. And this is a positive number, so that works out. Use identities to simplify secant x, cotangent x, sine x. So with problems like this, you're not necessarily going to know where to get started and where to go from. But the identities that you have, if you apply them, they're going to get you, no matter which ones you choose, you're probably at least going to get moving some direction. So for instance, the secant of x, I know that that is equal to 1 over cosine x. So I can change secant of x into 1 over cosine. Cotangent is cosine x over sine x. And then sine, of course, is just itself. Now, if you'll notice, I have a cosine in the numerator and denominator that would cancel, a sine in the numerator and denominator that would cancel, and the only thing left is just 1 over 1, which is 1. So the product of these three trig functions would always result in 1. So the question is, how will you know how far to take these problems to get them fully simplified? Well, in this section, you're either going to have it so where it's going to simplify down to either a constant or just one trig function, but something that's very much more simplified than what you started with. And a lot of times they'll give you these as multiple choice questions to where you're just simply going to answer the question with the correct choice, based off of how you've simplified. So you'll have some clues there. Later on, you'll have some problems where you actually just need to provide your work, but you'll have the beginning of the problem and the end of the problem given to you, and you're just supposed to figure out the details in the middle. And so you'll just show your work on those problems, and I'll show you how that happens later on. But for now, just know that they're going to either really simplify down, or you'll have a multiple choice problem. So write each expression in terms of sine and cosine, then simplify. All right, so this one, let's see what happens here. So if we write things in terms of sine and cosine, so secant squared is going to be 1 over cosine squared. Tangent squared is going to be sine squared over cosine squared. So I've written everything in terms of sine and cosine. To simplify, let's see what can be done. So first off, I'm going to factor out the 1/2 from this larger fraction. So that's that 2 in the denominator. So I can just write it as 1/2 out front. That's fine. In the numerator, I have a compound fraction. So I'm going to work on getting this compound fraction simplified. So what I'm going to do is I'm going to change this 1 into cosine squared x over cosine squared x. When I do that, it's going to become 1 minus cosine squared x over, now that they have a common denominator, you just put those over the same common denominator, so over cosine squared x. And then I have sine squared x divided by cosine squared x in the denominator. So what I'm going to do next is simplify a little bit further. I've got my 1/2 out here, and then we never divide fractions, we simply invert and multiply. So that's what I'm going to do next. So 1 minus cosine squared x over cosine squared x, that's the numerator. The denominator is going to be cosine squared x over sine squared x. So I inverted the denominator. So this fraction right here, I inverted it and multiplied. Okay, so now it looks like I have a cosine squared and a cosine squared here. Those will cancel out. So I now have 1/2 times 1 minus cosine squared x over sine squared x. Well, in this situation, let's see what we can do. I'm going to come off to the side and do a little bit of scratch work. So I know cosine squared x plus sine squared x is equal to 1. That's the Pythagorean identity. In the numerator, I've got a 1 and a cosine squared. They just happen to be subtracted. So let's see what happens if I subtract cosine squared from both sides of this equation. So it cancels over here, and I'm left with sine squared x equals 1 minus cosine squared x. So that is another form of the Pythagorean identity, which means I can substitute sine squared x in for 1 minus cosine squared. So this is 1/2 times sine squared x over sine squared x. These things are now going to cancel, and I'm just going to be left with the constant value 1/2. So again, something else that just simplifies quite a bit. So there's no trig functions left in this point.